Okay, so in this video I'm going to quickly run through how to invert a matrix. There are a few other videos out there on inverting specific matrices such as 3x3 or 2x2 matrices, but this video is the general technique and how you develop a general algorithm for solving the inverse of an n by n matrix. So first of all, what is the inverse of a matrix? Well, if you have a square matrix, such as the one we have here labelled by A, there is also defined the inverse of a matrix, which is labelled by a superscript -1, which is also 3x3, and that matrix has the property that when you multiply the original matrix by its inverse, you get the identity matrix. And just to be clear, the identity matrix is a square matrix where all the elements are 0, other than the diagonal elements, which are all 1. Okay, so which matrices can be inverted? Well, the first thing is that the matrix must be square for it to be invertible. So we have here a square matrix, a 4x4 matrix filled with integers. This can be inverted, but these two matrices here cannot. This is a 3x4 matrix and a 5x3 matrix. And as I said, the matrix must be square for it to be invertible. And the second condition is that the determinant of the matrix cannot be 0. It will become clear why this is the case later, but basically you can get the determinant of a matrix to be 0 if all of a row or all of a column contain elements which are all 0. It can also happen if you have two rows which are proportional or two columns which are proportional, and as we run through the technique and the algorithm, you'll see why that is the case. So before we start, we need to introduce the concept of the augmented matrix. This is simply just a notational thing more than anything else. It's basically just two matrices stuck together. So if we have our 4x4 matrix here, A, and we also have the identity matrix, we can form an augmented matrix by just connecting them together, and you have a line between them. That's the notational convention, and this is called an augmented matrix. We will need this throughout our technique. So when we're carrying out the matrix inversion, we will be basically, the technique we're going to employ is we're going to have an augmented matrix of our matrix of interest on the left and the identity matrix on the right, and we're going to carry out several row operations on our augmented matrix, and the idea is that we'll carry out operations in such a way that we'll end up with the identity matrix on our left, and whatever's left on the right hand side will be our the inverse of our matrix. So we're restricted to 3 different operations we can carry out, and the first one here is row switching. So I've just given an example here where you switch rows 2 and 3, and it's a very simple operation. You just have to swap every element of the row with the other row you're swapping. The second one is row multiplication, and that's where you take a row and you multiply every element in that row by a constant number. And the third operation is row addition. So this is where you take one row and you add another row to it, or a multiple of another row to it. So in this example, we've taken row 1 and we've added 2 times row 3 to it. So what that means is that you basically go through and you add the equivalent element from row 3 times 2 to that element in row 1, as we've done here. So these are the 3 operations we can carry out. Okay, so let's get down to the actual technique and the algorithm we're going to use. We start off with our matrix of interest, A, and the identity matrix, and we form. Okay, and what I've done here is I have basically taken a factor out the front of each matrix. It starts off as 1 divided by 1. The reason I've done this is just because it's a notation, just to make life notationally easy. We have an integer matrix and we're going to be doing a lot of division when it comes to our row operations, so we don't want loads of fractions inside our matrices. So if we have some common factors, we'll just keep taking them outside to leave integers inside of our matrices. Perhaps they'll be large integers, but it's a lot easier to put down, just in particular to make a PowerPoint presentation where you have integers within the matrix rather than loads of fractions. So that's the only reason we're doing that. Okay, so the second step is to go through the diagonal of our matrix on our left hand side and make sure that every element is 0. So what we do, we just go through, we start on the top left, work our way down and check that each element is non-zero. So in the bottom right we have a 0, so we have to carry out a row operation to remedy that. before we can start. It turns out you don't always need to do this. If you're writing a general algorithm to invert a matrix, you must, because there are certain situations where if you don't do this, the algorithm will fail. But sometimes if you have the 0 in the bottom right hand corner, for example, you may end up filling that position before you use it by carrying out other row operations. But to have a robust algorithm, you need to include this part of the algorithm into your code. So what we're going to do, we're just simply going to add row 3 to row 4 just to fill it up. We could do something else, but this is just a very easy way. We're just going to take the row above and add it to the 4th row. So we'll go through each element. So you take 8 from the 3rd row and 0 from the 4th row, add them together, you get 8. Similarly, 3 plus 0 is 3, 8 plus 1 is 9, so on. You just fill up the augmented matrix, and there we have it. So we have a matrix which now has has non-zero elements in all of the diagonal positions, and we've also changed our augmented matrix slightly. Okay, so the 3rd step in our algorithm is to make all the diagonals equal to 1. So the way the process continues is basically what we're going to do. We're going to go down the diagonal, set each element equal to 1, and then go down the column underneath it and set each of these elements equal to 0 by carrying out row addition operations using the diagonal. I'm going to run through the whole matrix, so this should hopefully become clear as we continue through the video. So we start on the top left hand corner with this 9, we want to make that equal to 1. So what we're going to do, we're going to use operation number 2, which is row multiplication. So we need to multiply the first row by some factor labelled x to make this 9 equal to 1. So we can just simply do that by having an equation here. We can say 9 times x equals to 1, because that's what we desire. Rearrange, and of course you get x equals 1 over 9. So what we're going to do, we're going to multiply row 1 by 1 over 9 and apply this row operation to the entire row. So I'm just going to go through each element. 9 times 1 over 9 is 1, and we just divide basically every element into row by 9, and you get this fractions here. And of course, as usual, you have to go through the whole matrix, both the left hand side and the right hand side. Okay, so there we have it. We have carried out our first operation. We have 1 in the top left hand corner. You notice we have some fractions here, and as I said before, just for the sake of keeping the matrices tidy, just for the sake of this video really, we're going to take a factor out. So we can just take this factor of 1 over 9 out the front, like so, and we're just left with integer matrices. So basically we just multiply everything inside the matrices by 9 and take a factor of 1 over 9 out the front, and we have to do it to both matrices, of course. Okay, so step 4, we now have 1 in the top left hand corner, or it's now written as 9 over 9. As I said before, you now have to go down the rest of the column and make every element equal to 0. And you do that by carrying out a row addition operation using the diagonal you just changed. Okay, so what we need to do then is take row 2 and add some factor of row 1 to it to give us 0. So this is r2 plus some factor we're going to work out, x times r1. So to work out what x should be, we can just say, okay, we have 27 over 9, and we're going to add x times 9 over 9 to it, because the 9 over 9 comes from the 1, 1 position, and we're going to set that equal to 0. And then you just go through the algebra, rearrange the equation, and you get x is equal to minus 3. So what we're going to do then, we're going to take row 2 and subtract 3 times row 1 from it, and that should give us a 0 in that position. So let's go through and do that. So we start off with the first element. We have 27 minus 3 times 9 is equal to 0, and that's what we want, of course. And then you have to go through the rest of the row of the augmented matrix and apply the operation to the thing. So we're just going to go through that. So you can pause the video if you want to check all these values, but I'm just going to run through it, and that's what you're left with. So we have now a 1 in the top left hand corner and a 0 in the position below. Okay, so what do we do next? We continue working down this column, setting every value equal to 0. Okay, so in this case we're looking at row 3. So basically we want to add to row 3 some multiple of row 9, which gives us a 0 in this position. So as before, we basically say 72 divided by 9 plus x times 9 over 9 is equal to 0. Rearrange the equation as before, and you get x equals minus 8. So we're going to take row 3 and subtract 8 times row 1 from that, and that should give us a 0 in this position. So let's run through and do that. Indeed, 72 minus 8 times 9 is equal to 0. And we apply this operation to the rest of the row. So run through. 27 minus 8 times 7 is minus 29, sorry. 72 minus 8 times 5 is 32, and so on. I would run through, filling out the matrix, and there we have it. So then we just have to go down to the bottom element and work out what x should be. So it's 72 again, so we can just use the same algebra, and it will again be x equals minus 8. And as before, and as always, we always take the position of the diagonal. We always take the row containing the diagonal we converted to 1 earlier, and use that for our row addition operation. So minus 8, and apply this to, we just apply this row operation to row 4 through, and there we go, we get 0. Okay, so now we have what we want in the first column. We have 9 over 9, i.e. 1 in the top left hand corner, and we have zeros in the other positions. So the next thing we do is we continue working through the diagonal and make the next element equal to 1. So this is the 2, 2 position. And in this position we have 15 over 9 in this position, and we want to find the multiple. When we multiply the second row by some term x, it will convert 15 over 9 into 1. So 15 over 9 times x equals 1, that's what we want, therefore x of course is 9 over 15. So as before, we just apply this operation, go through the row, multiply every element by 9 over 15, and indeed we get 9 in the diagonal position, and we fill up the rest of the augmented matrix. So this is what we're left with. We have 1s in the top left and the 2, 2 position on the left hand side, and on the right hand side you notice we have some fractions here. We have minus 9 over 5 and 27 over 5, so just to keep things tidy again, we're going to take the 5s outside, so that gives us 1 over 45 as the factor out the front of the matrix on the right hand side. Okay, and as before, we just have to work down below this position and make all these elements equal to 0. So we've got minus 29 here, and we have to add some multiple of the second row, because that's the one we've just operated on. This is the diagonal we just operated on to make it 1. We have to add some factor of the second row to row 3 to make it equal to 0. So as before, we just use this equation, minus 29 over 9 plus x times 9 over 9, rearrange, and we get x is equal to 29 over 9. So we're going to take row 3 and add 29 over 9 times row 2 to it. Okay, so let's go through and do that. And there we go. We have a 0 in the position we want. Okay, let's go to the position below. Again, it's minus 29, so I'm not going to dwell on too long. The equation will be the same. We have x is 29.9, and let's work through the matrix. And there we go. So we have the first 2 columns now complete. We have a 1 in the diagonal positions and zeros in all the positions below. So let's continue working through our diagonal. I'm going to go a little bit quicker now because you get the general idea, but you can always pause the video if you're unsure of any of these steps. So in this case, we have a value of x is equal to 3. If we multiply that row by 3, we will get 9 in the matrix, i.e. 9 over 9 if you include the factor out the front, which is equal to 1 of course. So let's go through this row, times every element by 3, and there we go, we get a 9 in position. Okay, and then as before, we have to take all the positions below in the same column, and there's only 1 left, and carry out a row addition operation using the third row this time to make that equal to 0. So I won't go through the details, but we're just going to, in this case, we're going to subtract 4/3 of row 3 from row 4, and that will give us what we want. Okay, so let's do that. Apply operation every element. And there we go, and we're just left with the bottom right hand diagonal we need to make to 1. So let's do, as before, we carry out a row multiplication operation, and as you can probably guess, we need x to be 1 over 10, so we just need to multiply the 4th row by 1 over 10, which we will do, and there we have it. So we have all of our diagonals equal to 1, and we have these factors of 10 on the right hand side now, so we're going to take those back out once again. So we have some rather large integers here, but it's better than loads of fractions. Okay, so you can sort of see what we're doing here and how this algorithm is progressing. We have the bottom left hand side is now as we want as for the identity matrix, and on the right hand side we now have some numbers in these positions, so you can sort of get a feel of the fact we're inverting it, yet we're still left with some numbers in the top right hand corner of our original matrix, and there are still some zeros on the right hand side of what started off as the identity matrix. So what we need to do, we need to go through backwards now and basically reduce all the other elements to 0, and we just carry out row addition operations as before, but this time we're working up and we must use the diagonal position once again for our multiplier. Okay, so let's start with this position here. We have row 3 and we must add some factor of row 4 to it to give us 0. So we have a minus 90 in this position here, and we need to add some factor of 9 over 9, which is the value in the diagonal position. And once again, we work through the algebra and we find the factor's 10. So what we need to do, we need to add 10 times row 4 to this row, and that will give us a 0 in the position we want. So let's run through and do that. So we have some zeros here, making things easier, and get to the position we want, and we get 0. And we continue to go through, and there's a little bit of cancellation here, which simplifies things. And we get some zeros on the right hand side. That's just coincidence. Okay, so continue up this column, carrying out the same operations. We missed that step, of course, because there was a 0 there already, so we don't need to do anything. And we get to the top right hand corner, and we once again add some factor of the 4th row, which will give us a 0 in this position. So we work through it. In this case, we find it's minus 2 over 3. So we have to subtract 2/3 of the 4th row from the 1st row to give us a 0 in that position. Let's go through and do that. And there we have it. So that's that column reduced to zeros. So you can sort of see the way this thing works now. And we just have 3 more positions to do. We have these 2 elements we need to make to 0. So we have a minus 9, and we, in this case, have to use the 3rd row because that's where our diagonal is. So work through the algebra and find x is equal to 1 in this case. So all you have to do is just add the 3rd row to the 2nd row, and that will eliminate that minus 9 there. So let's go through and do that. And there we go. So we are left with a 0 in that position. Continue through the algorithm. I won't go into the details of the last 2. It's all straightforward. You can pause the video if you want to. Basically work through, carry out the row operations. Keep going through. And there you have it. On the left hand side we have 1 over 9 out the front and a matrix containing just 0s and 9s in the diagonal. Of course, you can just take that factor of 9 back inside, and there we have it. We have the identity matrix on the left hand side. So that indicates that we're finished. We have our solution, and on the right hand side we have this matrix here, which is 1 over 450 multiplied by this matrix, and by definition this is the inverse of our original matrix. So it looks a little bit messy. It may not be immediately clear, but if you look at these numbers, there is actually a common factor of 9 in all of them. So you can take out a factor of 9 here and reduce the fraction out the front to 1 over 50, and you're left with this matrix here. This is the matrix of the lowest common denominator we can find. So this is our result. So finally, the way to check that the inversion has been successful is you take the inverse of the matrix which we've calculated and our original matrix, which is up here on the top right hand corner, multiply them together, and what you find is that indeed you do get the identity matrix. So that is the end of the algorithm, and that's how we do it. Before I finish the video, I just wanted to quickly mention one other thing. So imagine if you're watching this, you probably intend to make some sort of algorithm to carry out matrix inversion on large matrices, large square matrices. When doing so, you have to bear in mind one particular fact of most, in fact, all programming languages, and that's floating point errors. So just to illustrate this point, I'm just going to use this example here. We have 3 values, A, B, and C. They're 3 fractions. So if you multiply A and B together, that's 1/3 times 1/7, you're left with 1 over 21, which of course should be equal to 1 over 21, the variable C. So you subtract the 2 and you will get 0. However, if you write this up as some code unfortunately you'll find that this is not quite what happens. So here I've just coded up the same thing. We have 3 variables as floats, and you define a result which is a times b minus c. So a times b should be 1 over 21, so the result should be equal to 0. However, what will happen is if you evaluate these equations, you will find there's a rounding error at the end of your fraction. So if you actually carry out the result, if you carry out this operation using, in this case this is C++ on a Windows machine, you find that the result is actually very small, but it is not 0. You can reduce the inaccuracy by using doubles, but it will still be non-zero. So how do you get around this issue? Well, there's a couple of things you can do. Either you can just ignore it, which is what a lot of people can do. It depends what you're doing. If you're implementing the matrix in some other code, and to a very good approximation, 2.6 times 10 to the minus 9 is approximately 0, and that's perfectly acceptable. But if, for example, your code has some checking where it needs to check that the matrix has been inverted, for example, when you want to check that you have the identity matrix, then your code could well fail. That's if you use an operation, comparison operation to say if a certain element is equal to 0. So what could you do? One thing you could do is you could have some sort of threshold where you define a variable below which the magnitude of your result, if the magnitude of your result is below this threshold, then you can set it equal to 0. That's one way of doing it. Although, it depends what you're trying to do. If you want to use this for a general matrix solver, and sometimes you have very big numbers and sometimes you have very small numbers, that's not the best way of doing things, because you're going to have to redefine the threshold every time, and it may not be appropriate. Another thing you could do is perhaps instead of just using floats or doubles, you could use something like a fraction data structure, where every time you do some division by an integer, you'll preserve the integer in the denominator of your data structure. Now, I mean, this could potentially work if you're just working with integers. If you're working with irrational numbers, this again may fail depending on the exact details of your code. So as long as you're aware of it, it's not a particularly large problem, but it can crop up, and you may find your code will tell you your matrix has not been inverted when indeed it has. It's just an error in floating point arithmetic. So that's the video. Thanks so much indeed for watching, and I hope it was helpful.